detail of the research. Now you're recording back. Okay, good. I'm gonna talk about something more important than my research. Yeah, it's enough with the introducing me. I'm gonna talk about PhD student and mental health. Yes, it's really important. Yeah, mental health issues are there. It doesn't matter we ignore it or not, it is there. There is a growing cry for help from especially PhD students across the world who are struggling with significant mental health issues. Especially a very recent study, just November 2019, Wilson used more than 6,000 PhD students from all over the world, and 40% of them were international in the study, in the country that they were studying. And he showed that although 38% of them are still satisfied with the making decision to pursue a PhD, 45% of them confirmed that the level of dissatisfaction got worsened during the PhD. Oh, what happened? What were the reasons? Huh? Another Nature study, again recent, 2008, from Evans et al., using more than 2,000 PhD students and master students all over the world, showed that prevalence of the anxiety and depression is something really important among the postgraduate students. 41%, 39% for the anxiety and depression respectively. It's not a good news. It affects work-life balance. Look at the percentage here. For the anxiety and depression, people with anxiety and depression, unfortunately, it happens mostly for female, and for transgenders more. Yeah, obviously, we're not still good, and people are still afraid of revealing their sexuality and the gender of them. Many of the people with anxiety and depression confirmed that there was no good mentorship, and they didn't feel valued by the mentor that they had. Oh, there are some reasons that we can see why we have mental health among PhDs. It's odd. It's odd that universities ignore mental health problems. They don't want to talk about that. Maybe they don't want to spend money on that. But yeah, it disappoints me. It's not good. What are the reasons for that? One of the reasons can be toxic supervisions or toxic supervisors. Fortunately or unfortunately, there was a study showed that 65% of the PhD students identify mentoring or advising as a main factor in the PhD completion. Okay, it can be good or bad news because a supervisor can make or break a student regardless of the standard of this, okay. Another reason can be missing family. Been there a lot, maybe every day. I'm gonna quote Mariam, which was an international student from First Nature study that I showed you. She said, I struggled a lot in my first year. Here you sister. I started having anxiety attack. Wanted to quit everything. All of us been there, huh? Another reason, being overwhelmed. Actually, you are making yourself overwhelmed if you work a lot. I mean, in the First Nature study that I showed you, 76% of the students confirmed that they work more than 41 hours per week. This is not good. You're losing the work-life balance, okay? And all of them in the paper mentioned that they got this from the pressure that they feel in the environment that they are working, from the people in the department. This is not good. Don't forget, a PhD should never come at the cost of your mental health, guys. Another reason, I know nothing. Oh, you hear from the PhD student a lot. Me neither, I know nothing. I know nothing. Actually, it doesn't matter if you know nothing or not. You're the engine of all of the universities. You should be proud of yourself. You're the most important people in the universities. Universities are literally nothing without you. So you're the engine. Be proud of yourself. And hey, you've been hired to learn. You're not Einstein. It's not like someone look for an Einstein and say, hey, Einstein, come and work with me as a PhD student. No, you're here to learn. You're here to become an academic person and learn how to research, okay? So don't worry if you know nothing. Me neither. Some other reason, second language. Been there a lot. Be nice people. Be nice to the people who are, you see, second language is settling now, who are in second language, especially if the first language doesn't have the same roots like Latin with the English language. Actually, we are doing great. I'm going to tell you a good tip for the second language people. A little bit of alcohol make you Shakespeare, actually. Yeah, the Shakespeare. Yeah, think about that. Feeling unvalued. Yeah, not getting enough support. Have no publication. Who's counting? Doesn't matter. No one understands me. Me neither. And some other reason that you may mention after my talk. Okay, so what? What's the solution now? Don't worry, every problem has a solution. Look at this guy with this silly, even he has some solution. Yeah, first, accept that PhD is a big deal, okay? You're doing PhD. This is big. You decided to pursue education and get a PhD. That's why many people don't pursue education like this. And they say, I don't want to do PhD because they don't want to feel any pain. Okay, as a PhD student, accept a little bit of pain, not more than that, okay? But remember, pain is temporary. Doctoral degree is forever. And if you don't see that much support, if you see terrible behavior from your supervisor and you think, okay, I have no one, this PhD is not gonna be finished, okay, I'm gonna quit. Okay, stand in front of the mirror, look at yourself and say, okay, this is my thesis. My name is written on the front of this. I need to become the driver, Only your name would be there. Think about that. Become the driver, make the thesis, make the PhD finish. Write down all what you have done so far. Give yourself some credits. In Newcastle, we had to fill some progress report every 6 months, which was a real pain. But I actually took advantage of that by writing down what I had done till that time, and every little thing, right? Every little thing, every little step, every line of code. And then at the end, you will see, oh, this paper is full. I did a lot. I'm a good person. Give yourself some credit. Appreciate yourself. Be proud of yourself. You're the engines. I told you, huh? Make some group talks, mostly with PhDs and postdocs. Those people have similar situation with you. They can understand you. Okay. Talk about problems instead of bragging on the success with that group talking. Okay. Complain more. Let's gossip. Actually, my favorite author, Noah Harari, in the Sapiens book, mentioned that in the wake of cognitive revolution, gossip helped Homo sapiens to form larger and more stable bands. You know what would happen if you start a gossip talk with your colleagues? You will see that you're not alone. Everyone is struggling. So it's beautiful, isn't it? Speak. Don't be shy. Complain. Don't be afraid. This is your right to complain as a human being. And remember, try to enjoy your PhD. This is your last chance to be a PhD student, to be a student. You're going to miss it a lot. I already missed it. I was a student just 6 months ago, or maybe less than that, but I already missed it. It's like it was 10 years ago, or maybe, because I missed it a lot. So this is your last chance to be a student. Enjoy it. And actually, the good thing about being a student is that you can bring many excuses because you're a student, okay? So use that and enjoy this. And what if I have mental health issues? Everyone has it, believe me, a little bit, a different dose, but everyone has it. First, try not to ignore it. Accept it. Okay, I think that I have this mental health problem. I should figure it out. And hey, it's not embarrassing to seek help for your mental health. Actually, to me, it's so cool. It's so open-minded. It means that you take care of yourself. I always bring this example that all of us got cold in our life a lot. And sometimes we went to doctor to get a pill that even we can buy it from Woolworths. So we take care of that cold thing, but we don't take care of mental health. That's the problem, huh? Unfortunately, in that Nature study, which they showed that just 36% of the students have sought help for their mental health issues, and unfortunately, just and 80%, 18% of them did this at their universities, and they were not that much happy. Don't be that. Don't be like that. Seek help. Enjoy yourself. And I made this circle last night. I'm gonna call it help circle. It's very important. Let's make this help circle in your community, among the PhD students, postdocs, even your friends, your families. Start with asking some questions from your friends. Are you okay? If you ask this today, your friend would ask this tomorrow. How can I help you? You're making a help circle in your group. It's okay if you're not okay. I'm here for help for you. I'm listening. How can I help you? Let's talk. Okay, in fact, I'm gonna make this help circle right now at RSES, which is 16 September 2020. We're gonna make this help circle if you join me. I'm gonna tell all of you, I'm gonna ask all of you, are you okay? How can I help you? I'm here, I'm a good listener. I'm gonna listen to everything from you. Let's talk, let's go for a coffee. Let's complain, that's okay. If you're not okay, okay? Join me if you like. We can make this help circle work at RSES among us, and we enjoy our company. This is the picture from the thesis submission day. I was the happiest girl in that day, and I wish that day and that a smile for all of you. I'm done.
All right. Thank you very much for that, Nadia. It was something we all needed to hear, I'm sure. Personally, I can relate to a lot of them. Thank you for the talk. And we're gonna move on into the student presentations. So if you can stop sharing your screen. All right, so the first person presenting today is Boss. She will be presenting on electrifying opals. Go ahead.
Okay, can everyone hear me?
Yes.
Okay, brilliant. All right, I'm just going to attempt to share my screen. Okay.
Oh, by the way, a quick announcement. If there's any academics watching, please fill out the judge form and send it in today right after all the presenters finish their talks, so, because we want to present the awards 10 minutes after we're done with the presentations. Thank you. Go ahead, Bas.
Is it showing up correctly?
Yes.
Okay, brilliant. Hi everyone, my name is Boz, or Bojana Pashic if you would like to try and pronounce that. And today I'm going to be talking to you about electrifying opals. This is a topic that I've been working on in the last year or so, and I will be giving you a quick overview of the progress that I've made so far. So first, electric opal. The reason why electric opal is called electric opal is because of its extremely high uranium content. And this is due to its incredibly unique structure in that it is not a typical opal as we know it. It is actually more similar to a glass. Now, the uranium here, the source of the uranium here is uranyl molecules that are dispersed within the structure. And the reason why this is so special is because it actually exhibits daylight luminescence. Gem quality specimens will be bright green in daylight, and some of these specimens can actually fetch up to $10,000 US per carat. It's incredibly rare, and it's the only known locality of such a type of opal. A little bit more about the structure and why it's so different to typical opals that we may know about is that up here in the left-hand side is the structure of electric opal. It displays more, these are SEM images, and it displays more of a glass-like structure. These are just cracks, as opposed to a precious opal as seen here. So this is the type of opal that we would be used to seeing, which is the type of lightning ridge or Ethiopian opals. And you can see that these spheres here are actually perfectly ordered silica structures, which don't exist here. Now, electric opal is found in one location and one location only, and that is here in Zacatecas in Mexico. We are not actually allowed to disclose the location. It's really like cool and secretive, but the opal occurs here in between in this tuff above some sediments. Now, the formation of this is quite interesting. It's thought that it formed basically from a giant devitrifying volcanic pile where you had groundwater circulating, interacting with unstable silica glass, which then redissolved and reprecipitated into an opal. The thing with this is that this is not typically how we would think about opal being formed. And a highlight, as electric opal is, typically just will, from a gas, sublime onto a cold surface, and it won't contain the amount of uranium it does, or in fact many other things. It'll just be a coating. Whereas this had time to go and scavenge uranium from other minerals within the volcanic pile. One of the things that I did first when I got this was chuck it on an SEM and have a look at the CL. If you look at this image here, you can see an incredibly intricate CL pattern, and CL stands for cathode luminescence. The cathode luminescence here, this brightness corresponds to increased uranium concentrations, and the dark bands here correspond to low uranium concentrations. These are so bright because of the extremely high activation energy required, like emitted from uranium. And if you can see here, there's actually detail in here, but it's so bright that you can't actually discern what it is. So what I did next to confirm my suspicion that this was uranium doing this was I took it on an electron microprobe and did some mapping. And one of the interesting things that came out of this adventure was that we found that there was correlating calcium with uranium. So these maps here show counts of uranium. So this is semi-quantitative and not qualitative, not quantitative, it's semi. So these are just counts of uranium from during the analysis session. And the warmer colors correspond to higher concentrations of uranium or uranyl, as opposed to the colder colors, which correspond to low concentrations. What's interesting to see about this is that there seems to be multiple generations of where uranium is, which is quite an interesting feature of this. But what struck me the most was this correlation with calcium. So what I did next is I went on a laser confocal microscope, which came here as a part of demonstration. And what a laser confocal microscope does is that it looks at different wavelengths and images through a sample. And if that sample is excited along this wavelength, it'll emit back. And so this is the result that we get from the area that was mapped on the probe and taken pictures of. So I hope it works. Yes. So you can see as we're going that the brown in this movie is actually correlated to sediments or pieces of the host rock that are stuck in the opal. And then we can see these bands of pretty much uranium radiating from here. So that kind of tends to give us an explanation for what is actually causing those interesting CL and mapping patterns. Oh, there it is, it's going up all the way up to the surface. And there's a big giant crack there, so we'll ignore that. But basically what this showed is that we have a 3D problem when we're imaging with CL, and we're actually seeing the effects of what I believe are various nucleation points on the host rock. after we did some mapping and after we took some images, what I did next is I actually did some quantitative analyses, and these quantitative analyses showed something quite extraordinary. It showed that the calcium and the uranium were on a molecular level correlating almost 1-to-1. This is the first time that this has been reported in or observed in an opal of this sort, or in general. I haven't seen this correlation before. And initially the thought is that all of the calcium correlating with the uranium was a result of common lead contamination. But when you look at the lead concentration versus calcium, you can see that there is a lot less lead than calcium. The other thing that I should note with this analysis is that the detection limits for lead on the electron microprobe are quite a bit higher than on other methods. So the reason why this pattern is so low in data points is because a lot of the analyses were actually below detection, as opposed to here, which is just swimming in calcium and uranium. So to discern our common lead problem, we went on the laser. And what we saw here is pretty much essentially the same thing. You see that calcium and uranium have a really strong correlation, as well as 206 lead with calcium. The analyses from the laser actually show that there is virtually zero common lead. It was all below detection. And this, then, if we all know from uranium lead geochronology, we know that the daughter product of 238 uranium is 206 lead. So all of this lead and calcium correlation is the result of the daughter product of uranium, which is why it's correlating with the lead. So there's no common lead interferences in this. What I did, I also checked this with the shrimp when we did the dating, and I'm pretty convinced that there is no common lead in this. So uranium lead dating in opal has been done before, and it's been done on the basis that oxidized groundwater precipitating opal is actually enriched in uranium relative to thorium. And so the fine lamellae as well showcase in sequential growth and changes in uranium concentration within the groundwater. So you can sort of date the changes of geochemistry or geological events. The standards they used in this analysis were M21277 and BZBB, both which have been independently checked with TIMS analyses for their dates, and that have been used in shrimp dating of uranium of opals. So when we looked at the Concordia for that, so there is once again no common lead. Yeah.
I'm sorry, I have to interrupt, but we just run out of time. Maybe
really? Oh, I'm so sorry.
Comment on it later today at drinks. You can just finish just talking about the results, but we have to move on. I'm sorry.
Oh, okay, no worries.
But it was a very interesting talk. If anyone has any questions, please put them on the chat, and I'm sure Buzz will be happy to answer them through there. And if you stop sharing your screen, please.
Yeah.
Okay. So the next person presenting is Victor. He is presenting on what can we know about modern global warming by studying Paleocene, Eocene thermal maximum. If Victor could please start sharing his screen.
Yes.
Thank you.
Can you see my screen?
Yes.
So, hi everyone. My name is Victor. I'm a student in the Paleoenvironments group. My talk is called What Can We Know About Modern Global Warming by Studying the Paleocene Thermal Maximum. As you may know, we are in a period in which the global temperature increases are mainly linked to anthropogenic activity. As you can see in this figure, since the Industrial Revolution, the global surface temperature has tended to increase, and it is expected to reach dramatic levels as the warmest global surface temperature of the warmest period in the last 65 million years in the next 200 or 300 years. The fastest carbon release rates for this period of hothouse may have been as fast as 1 petagram of carbon per year. But for the current anthropogenic carbon release rates, these estimates for carbon release rates have been estimated to be 10 times faster, which has led to irreversible climate change. However, it doesn't mean that the climate is going to be warm permanently. After global warming, carbon sequestration processes are expected to storage all of the carbon in carbon reservoirs. In carbon reservoirs. Essentially, what carbon sequestration does is taking the carbon of a carbon injection, which leads to a reduction in the global ice content, which leads to a temperature increase, more precipitation, which means hydrological cycle condition enhanced, and finally, it increases chemical watering, which leads to cooler climates by a carbon sequestration mechanism. The modern global warming and its potentially dangerous carbon release rates have led to create new technologies which are expected to accelerate carbon sequestration, new estimates about how effective nature is for carbon removal, and new environmental policy which seeks to improve technological advances related to carbon sequestration and, of course, reducing CO2 emissions by themselves. Despite all of the importance of carbon sequestration, we don't know clearly the timescales of carbon sequestration mechanisms after rapid warming events as the current one and past paleo events in the Cenozoic record mainly. This is reflected in the PTM, which is the Paleocene thermal maximum, and is an spike in the temperature here. This event is identified in the geological record, in the sedimentary record, by a negative carbon isotopic excursion in carbon stable isotopes, which you can see here. And this event was so dramatic because it generated global ocean acidification, ecological disruption, mainly linked to foraminifera extinction, mammal migration, the forest was with the spread. But we don't have clear age estimates about the PTM. So we don't know clearly how long was the carbon removal period that the climate system needed for recovering for a carbon injection as high as the PTM, which, as I told you, was the warmest period in the last 65 million years. To solve this problem, we created a probabilistic astrochronological age model for high-resolution carbon stable records of the Contessa Row section. This section is located in Italy, consists of carbonates, and is so special because it was deposited over the carbonate compensation depth during the PTM. So it was less affected by global ocean acidification than other sequences around the world. Just to clarify a point quickly about what we do, we know that the climate system is partially controlled by the orbital framework. Sedimentary rocks record orbital influence. This influence is mainly controlled by orbital components, which are essentially eccentricity, which is here, obliquity, and precession. Based on the sedimentary record or any property of the sedimentary record, we can create H models with these orbital components. We can extract a frequency from a power spectrum and relate cycles in the sedimentary record, like here, the line that you can see, and relate these cycles to orbital solutions, which are in terms of H. So we can create floating chronologies. We made that based on Monte Carlo simulations to generate H models with errors for the ages, which is so new in our area, because as you can see, astrochronological H models are only one line. So in our H model, we were able to identify that the difference between the PTM onset, which is here, and the CIE peak, which is here, is 15 kiloyears. And it shows approximately the duration of the first carbon release that triggered the PTM. So we were able to calculate the carbon release rates for this period, and we identified that our estimates are smaller than the previous estimates calculated for this event, the estimates that I showed you at the very beginning of this talk. So we can infer that anthropogenic global warming could be even more dramatic than we used to think. Additionally, we found two CIEs, which are here and this one here, that are related to two carbon release pulses. And we identified that each carbon release pulse is followed by a period of rapid carbon sequestration, which are shown by enrichment of the delta 13C signal, this one and this one. We realized that we can adjust the PTM recovery to exponential functions. The half-life of these exponential functions depends on the carbon injected and the carbon flux rate in the Earth surface carbon cycle. The most interesting thing here is that the second CIE related to the second carbon release during the PTM has an exponential decay function that is seen in the range of the modern carbon cycle conditions, which show us that during the PTM, we already had carbon cycle conditions similar to the modern world, which is so worrying and shows our influence over modern global, over the modern climate. We identified that the PTM ended approximately 120 or 140 kiloyears after the second injection. So we can infer that the Earth would require approximately more than 100 kiloyears to recover from a climatic perturbation. So we can conclude fastly that carbon injections are followed by rapid recovery periods of, it means rapid carbon sequestration rates that are in between 20 and 30 kiloyears. However, the long-term recovery for a climatic perturbation is more than 100 kiloyears. As you know, the modern global warming is in human scales, and these processes are in geological scales. So we remark that natural processes are not going to be able to reestablish the climatic perturbation that humans are generating. So as other studies and researchers have claimed around the world, we say that technological advance and political action are strongly necessary to face climate change. And that's it. Thank you.
Thank you very much, Victor. We don't have time for questions. If anyone has any questions, please feel free to put them in the chat. And the next person presenting is Riley. He's presenting the thermodynamic modeling of low temperature mineral formation in the Tagish Lake meteorite. So if you can please share your screen. Thank you.
Well, thank you. Hold up, just let me get this gizmo up and running. That one. Yeah. Lovely. Can everyone see that?
Yes.
Lovely. All right. Good afternoon, everybody. Today I'm going to be talking to you about the thermodynamic modeling of low temperature mineral formation in the Tagish Lake meteorite. So let's get right into it. Hold up. Now, the Tagish Lake meteorite is a carbonaceous chondrite, and it's full of what we call extremely primitive material. So that means that it hasn't been heated, it hasn't been melted, and it hasn't been crushed since it was all swept together at the start of the solar system. The Tagish Lake meteorite's also the most carbon-rich meteorite we've ever discovered, so it's not surprising that it's also got really high organic content. Now, if you take a look at the picture of a hand sample on the right, you'll notice that the meteorite itself is made of this friable material. It falls apart in your hands. So the meteorite didn't land with a thud. It sort of shattered in the upper atmosphere and rained down as a bunch of pebbles of dust, which is terrible because next time it rains, you won't be able to collect it. Except this landed on Tagish Lake, while it was frozen. So all this dust and all these little pebbles landed on this frozen lake and people were able to go out and collect them. Really good. A very unique specimen. We've never seen anything like it before. Now, like a lot of meteorites, Tagish Lake has high and low temperature minerals and they're all mixed together. So we'll just take a quick look at those. Now, this is a BSE image of the Tagish Lake meteorite on the right, and it's got a few components. So the big one is the fine grained matrix. So you can see it's got phyllosilicates, they're the gray bits. It's got carbonates, they're pointed out by the white arrows. There's organic material in there, but it's a bit hard to see because it's in black. And there are also iron minerals, and they're the little white bits. Now, all of these are really low temperature minerals, which is great, except it's also got silicates, it's got olivines, it's got pyroxenes, high temperature minerals. They're all mixed together. It's kind of crazy. But my favorite part is the chondrules. Now, these are formed from droplets of silicate melt that have cooled in the protoplanetary disk. And the ones in Tagish Lake are exceptional. I'll get into them in a minute. Now, Tagish Lake also has calcium aluminium rich inclusions, but I couldn't find any in that picture. So here's a separate one. Now, those chondrules, they're utterly unique. As this is a BSE image on the left and a drawing on the right that makes it a bit easier to see. But Tagish Lake's chondrules have this unique concentric rim structure. So you've got a chondrule core made of olivine, which is surrounded by a layer of phyllosilicate, which is then surrounded by another layer of carbonate. It's amazing. It's utterly unique. Now, we know that olivine can react with water in the protoplanetary disk to form phyllosilicate, so it makes sense how that first rim forms. But we're not quite sure how that carbonate rim forms. I mean, the reaction below is a possibility, but we still need to look into it. So, my question is, how did the carbonates form? Now, I've got three scenarios to look into. The first one is that they formed in the protoplanetary disk. So this is where you've got just bits of dust and gas all floating around before the planets formed. And since you haven't formed your planets, it'll be a solar composition. And because you're in space, you're at low pressure, 10 to the -4 bar. The second scenario is what's called a high temperature, low pressure environment. Now, this can happen on the surface of an asteroid if it's exposed to space, but the way cooler option is that you bash two asteroids together, everything heats up, you spit out a lot of gas and a lot of dust, and then while it's cooling down, you form new minerals. They call it an impact plume. It's pretty cool, but that's not going to be a solar composition. That's the same composition as Tagish Lake, and you're still in space, so low pressure. Now, the last one is high temperature processes within the asteroid itself. So inside the parent body, you can have heating, which causes the formation of new minerals. That'll be, again, Tagish Lake composition, but this is much higher pressure. This is going to be at about 1 bar. Now, it turns out it was a bit too expensive to send me to space to do this stuff firsthand. So instead, I did thermodynamic simulations. So I calculated what would be present at thermodynamic equilibrium using Gibbs free energy minimization. Now, this is not including kinetics. It's only looking at equilibrium composition. So I've got my multiple compositions, I've got the temperature and pressure ranges listed, and I've got to include all the phases and the thermodynamic data for them. That can be a bit tricky, but it worked. So let's get into the results. Firstly, the protoplanetary disk. Well, the carbonates are less than 1/1,000,000th of a mole% of the solids. That's what we in the business call not much. So no, you're not going to form your rims. You're not going to form many carbonates in this case. You can look at that graph on the right all you like. There's nothing there. Let's keep moving. All right, part two, the impact scenario. This is a much cooler graph. It's a graph of equilibrium composition versus temperature. And if you look on the bottom left, you've got the red line for the magnesium carbonate and the blue line for the calcium carbonate. Now I'll just zoom and enhance in the next slide. And you can see that the carbonates actually form a reasonable proportion of the solids that are formed, but only at low temperatures. Below about 50 degrees Celsius, you actually do form sizable carbonates. Cool, you can form carbonates through an impact. Now, our final situation is the temperature within the asteroid itself. Now, this is my favorite graph by far, so I'll just take a minute and zoom in a bit. You've got a great big broad peak for magnesium carbonate, you can see in red, and you've got not necessarily a peak, but a nice broad presence for calcium carbonate over a huge temperature range and pretty high amounts too. So you can form a lot of carbonates here. You can form over 20% of the solids, but more importantly, it's over a huge temperature range. Absolutely amazing. You can form loads of carbonates. So, just to wrap everything up, carbonate formation is thermodynamically favorable when you're looking at a Tagish lake composition, especially compared to a solar system composition. So you can form carbonates in impact environments and parent body environments, but that depends on the temperature. Now, remember, none of this takes kinetics into account. This is purely looking at the amount that forms in equilibrium. Thank you very much.
Thank you, Riley. That was very interesting. Does anyone have any questions?
Hey, Riley.
Hello.
Yeah, so your calculation demonstrated the carbonates can be thermodynamically stable in those two scenarios. But is there any hint how the carbon in its previous any form, any molecule, how can it be converted to carbonate? The carbon element, how it was converted to carbonate?
Well, it's actually interesting. It's interesting that you ask that, because when you look at the solar nebulae, you usually have a lot of methane and you have CO2 and CO. So in your actual disk, you can react with those directly. But
so seems that will involve many redox reactions.
Yep, and that's why it's so nice to be able to model it thermodynamically. It's a lot more straightforward, and thankfully you can use a computer system that models all of them for you.
Okay, thanks.
No.
We also have a question from Caleb on the chat. Which method do you think was most likely responsible for the formation of your chondrules?
Wow. Wait, do you mean the chondrules or the rims? The rims themselves, that's the sort of thing that people start to get in arguments over. So I'm glad I'm not saying this in a bar. But personally, I think that the impact scenario is rather convincing. But because this doesn't account for your kinetics, you really need to remember that the cooling history is a big deal. So depending on how fast it cools, you can stay at a different temperature for a different amount of time. So an impact scenario only has that really narrow temperature space to form your rim. So if it doesn't stay there very long, then you don't have time to form them. But I think it's impacts, but that might get me in a lot of trouble with a few professional meteoriticists.
Okay. You have one more question from Boss. Maybe you can answer it on the chat, because we have to move on to the next talk if that's okay.
Thank you very much. Thanks for having me, guys.
Okay, so the next person presenting is Kelly. She's presenting a new Southern Ocean radiolarian surface sediment database.
All right, good afternoon, everyone. I'm Kelly, and I'm a second year student kind of straddling the paleo environment and geochemistry groups here at RSCS. And today I'm going to talk to you about my work with radiolarians in the Southern Ocean. So basically, the overarching aim of my PhD is to reconstruct paleoclimate and paleoceanography for two regions in the Australian sector of the Southern Ocean: the Sabrina Coast in East Antarctica and the Tasman leakage near Tasmania. The primary proxy that I'll use will be past radiolarian assemblages found in sediment cores that are marked on the map. And to correctly interpret what radiolarian fossils tell us about the past, we look for patterns in their distribution and abundance in the modern Southern Ocean and try to figure out how the environmental parameters, responsible for these patterns. So broadly speaking, paleoclimatologists research past environmental responses to external forcings and changes in Earth's atmosphere. The reason we look to the past to investigate environmental changes that have taken place on millennial or multi-millennial timescales, and to see what Earth's climate was like before humans started recording observations and using instruments to measure climate parameters. Past climate knowledge can help us predict how Earth will respond to future climate forcings. So the way we gather data on climate in the past is to use climate proxies. These are records of past climate variability found in natural archives, such as ice cores, lake and marine sediments, and coral reefs. Several proxies can be found in one archive. For example, one marine sediment core can contain multiple geochemical and biological proxies, such as plankton microfossils, biomarkers, and ice-rafted debris. And climate proxies are used to reconstruct past environmental variables, such as air and ocean temperature, sea ice extent, and the chemical composition of the atmosphere. So I specifically work with marine microfossils, in particular radiolarians. And marine microfossils are basically the skeletons of former ocean-dwelling microscopic plankton that have settled to the bottom of the ocean and are retrieved when we take marine sediment cores. So examples that you may have come across include diatoms, foraminifera, silicoflagellates, and my favorite type, radiolarians. Radiolarians are marine zooplankton. They're generally 30 to 300 micrometers in size. There's 600 to 800 extant species, and in the very southern part of the Southern Ocean, I generally see 120 to 130 different taxa. The polycystine Nassalaria and Spumalaria orders are the radiolarians that I work with, and they have salacious tests. Their abundance and occurrence can be correlated with water mass characteristics like sea surface temperature. They inhabit all depths of the water column, unlike photosynthetic plankton, such as diatoms that stick to the surface, and they have been used as a paleo proxy for sea surface temperature. So now I've gone through a little bit of background. To jog your memory, my project aim is to reconstruct paleoclimate in these parts of the Southern Ocean. And the most important point here now on this slide is the third point. So to decipher what radiolarian fossils can tell us about the Southern Ocean in the past, first we need to look at modern radiolarian distribution and abundance patterns, and then identify the environmental parameters responsible. So the next two slides will be on some of my preliminary results. I'm using a new modern radiolarian census database compiled by Giuseppe Cortese. He's my co-supervisor and he's based at GNS in New Zealand. The database consists of radiolarian assemblage data from more than 200 Southern Ocean surface sediment samples. And I'm in the process of writing this data set up for submission into the Earth Systems Science Data Journal at the moment. I'm also using this data set to investigate Southern Ocean radiolarian biogeography and diversity. And I'm trying to determine if there are relationships with ocean parameters, such as temperature, nutrient levels, or salinity. So this map shows the sites that are included in the new data set. They're colored according to the biogeographic province they belong to. So each color represents a different biogeographic province. So unsurprisingly, there's a latitudinal effect. We have this southern circumpolar province here in blue, south of the polar front that encircles all of Antarctica. And there's some north-south partitioning in the Indian and Southwest Pacific Oceans as well. But what is most surprising and kind of a new discovery is that there is basin partitioning also. So there's very distinct provinces that belong to the Atlantic, Indian, and Southwest Pacific sectors. And looking at species diversity, here are the results using the Simpson's Diversity Index. I have tried other measures of diversity as well, and we do get similar results with all of them. So the map shows the sites. They're sized and colored by Simpson's Diversity Index. So the small orange dots represent lower diversity sites, and the large purple dots are the higher diversity sites. The Atlantic sector stands out as there's quite a sharp differentiation between low and high diversity sites. The scatter plot at the bottom here is the Simpson's Diversity Index by latitude. The points are colored by ocean basin and they're shaped by the zone that they belong to. For example, Antarctic zone, polar frontal zone. We can see that while diversity is increasing with latitude, that's unexpected. The latitudinal diversity gradient is quite a well-known phenomenon, but we can see that the rate of increase in diversity varies between the basins. So the Southwest Pacific has quite a flat diversity gradient, while the Indian and Atlantic sector very steep here, and this is in the subantarctic zone. So that's where diversity starts to increase. So next, I'll try to determine which environmental parameters are most responsible for the biogeographic partitioning and variation in diversity. This will help us understand which past environmental parameters radiolarians are best suited to reconstructing. The preliminary results do look interesting, and we're seeing that different environmental parameters are more significant in different basins. Then I'll apply this knowledge to radiolarian assemblages found in cores from the Sabrina Coast and Tasman sites. That's the end of my talk. If there's any questions, go ahead.
Thank you very much for the talk, Haley. Does anyone have any questions?
I can't actually figure out how to unshare my screen. Oh, here we go. All right.
Okay. Well, if no one has any questions, we can proceed to the afternoon break. We're gonna have a 20-minute break, and then we're gonna come back at 2:50 for the next presentations. All right, hello everyone. We're gonna start with the second part of the presentations today. Just a reminder, if there's any academics, can you please fill out the judge forms and send them in right after the last presentation so that we can choose a winner for today. You can send them to Jess. That'll be great. So the first person presenting today is gonna be Siji with the story of S-type granites. Are you here, Siji?
Yes, I'm here.
All right, if you can share your screen, that'll be great.
Yeah, but you're okay. Cool. Now, able to share. Can you see my screen?
Yes.
Cool. Perfect. So okay, just get started. Okay. Thanks, Lou, and thank everyone sticking out. I am Z. I'm a third-year PhD student working with in Campbell. Today, I will show you the work I did during my PhD about using detrital from model rivers to document the distribution of S-type granites through time. First, why we use detrital from model rivers? Well, zircons, they are physically and chemically stable across a wide range of conditions. So they could record signatures of parental magmas in which they crystallize. On the other hand, in modern rivers, eroded materials have experienced long time sediment recycling, which result in efficient mixing of sediments from various source rocks. Therefore, detrital zircons from modern rivers could be a combination of zircons from various types of source magmas. So this is a picture I took of by collecting samples of Seine River last year. And from these sediments, little zircons could be separated and analyzed for further studies. So over the past 20 years, our group has collected samples from over 50 world's major rivers, and over 7,000 zircon grains have been analyzed for their uramide age and trace element compositions. Then I want to give you a very brief introduction of what are S-type granites. So broadly speaking, granites can be classified as either I-type or S-type, depending on their source rock was predominantly igneous or sedimentary. And this classification was firstly proposed by Chapman and White in 1974, based on rocks in the Lachlan Fall bed in which Canberra is situated, and actually could find a memorial bench to Chapman and White between Jaeger 8 and the OHB in RCS. And there are many ways to distinguish them, but the way I use here is by the phosphorus content of zircons and the ratio of phosphorus to rare elements, which is based on the work proposed by Anthony and Andrew in 2017. To be specific, if we plot the phosphorus data distribution of zircon from typical I-type and S-type granites, we can see that zircon from S-type granites tend to have higher average phosphorus and a wider range of phosphorus concentrations than those from I-types. And this is the phosphorus data distribution of zircon from global rivers with an unknown proportion of zircon from I-type and S-type source. Here I use a mathematical model to calculate the relative abundance of zircon from S-type source in this unknown dataset. And here's the result. The Y scale represents the percentage of S-type zircons in the select age groups, and the values and the error bars represent the best fit value and the 95% confidence interval. And as you can see that Gondwana was the most important period for S-type granite production, whereas Akin was the least. And Rodinia is the last important period compared with Nuna and Gondwana. Another method I used is the correlation between rare elements plus yttrium and phosphorus. As you can see that there's a strong near one-to-one correlation for zircon from S-types, but not for those from I-types. And most of the S-type zircon tend to have higher phosphorus concentrations. So if we count zircons that fall within these two near one-to-one slopes, but also have higher phosphorus concentrations, say molar phosphorus higher than 15, 84% of S-type zircon are shown to meet this condition, while only 3% for I-type zircons. And the geological interpretation for this classification is that the near one-to-one correlation indicating various elements and yttrium are substituting zirconium via xenotime substitution, and the higher concentration of phosphorus can be attributed to higher solubility of epitite in periluminous melt. And the melt of S-type granites tend to be more periluminous than I-types. So then I plot all the zircon data from global rivers and then select all the zircons that fall within this area, which is defined as S-type zircons, and show their age distributions here. And data from different continents are shown in different colors. And again, as you can see that Gondwana was the most important period for S-type zircon production, with contributions mainly from Australia and Europe. Akin was the least, and Rodinia is the last important period. The discussion I want to focus on here is that why Gondwana was the most important period. To form S-type granites, 3 factors are very important. First, a high water content. Second, a near equal amount of coarse albite and potassium feldspar makes the composition in source region close to the minimum melting point. And third, a source of heat is required. Therefore, the most likely source materials for S-type granites are turbidites, which contain interbedded shale and greywackies. Shale provides water and potassium, and greywacke provides coarse and plate clays. And these essential components makes the sediments in the source region close to the minimum melting point to form S-type granites. And the sedimentary materials in turbidites are generally from erosion of high mountains. A modern example is the Bengal Fan, the world's largest turbidite deposit, which is produced by erosion of world's highest mountains, the Himalayas. And the rapid erosion of mountain chains that were produced during the continental collisions to form supercontinent result in thick deposition of turbidites, which are likely to be the dominant source materials for S-type granites. And the very high abundance of S-type zircons during Gondwana is a tribute to the very high mountains formed during this time. So this is a plot showing the pressure of metamorphic rocks through time. And there is a dramatic increase at about 650 million years, indicating the orogenic zones during Gondwana were higher and therefore capable to support higher mountains. And this is a figure showing these super high and super long mountains produced by collision between East and West Gondwana and the massive turbidites along the two sides. So in this site, the sediments were carried across Antarctica by big rivers towards Southeast Australia and produced massive turbidites there, which have been suggested as dominant source materials for S-type granites in the local beds. And in the other side, turbidites were produced along the margins of Western Gondwanas, and they have also been suggested as dominant source materials for S-type granites that crops out now mainly in Central and Western Europe. And these thick turbidites deposition locations correspond well with abundant S-type zircons in my result during Gondwana time, mainly from Australian and European rivers. To conclude, we think phosphorus content and the relationship between various elements and phosphorus could be powerful ways to distinguish zircon from S-types. And Gondwana was the most important period for S-type granites production, which can be attributed to formation of extensive turbidite bands. And that's it. Thank you so much for your listening. And I'm very happy to take any questions.
All right, thank you very much for your talk, Xi. It was very interesting. unfortunately, we do not have time for questions. If anyone would like to put them to the chat, and we're gonna move forward to the next presentation, which is by Beck. She's gonna present mitigating thermal noise in GRACE accelerometer observations. If you can please share your screen.
Yes, when I figure out how to do it. Okay, do you want to turn off your... Okay. Mute your computer. No, I mean the output, so that there's no noise coming out. Sorry, everyone. Okay, so for 15 years, the GRACE, or Gravity Recovery and Climate Experiment, the satellites mapped the Earth's gravity field by orbiting around the Earth while measuring the distance between the two satellites, which varies according to the changes in strength of the Earth's gravity field below the satellite. And that's represented by that red line there. So the Earth's gravity field has both static and time-varying components. We're mostly interested in extracting the time-varying, or what we call the temporal components of the gravity field, which mostly varies according to variations in masses of water as they move across the surface of the Earth. So in this video, for example, you can see that we have significant masses of water varying in areas like the Amazon basin, and that's a seasonal signal there, but we can also see as the time series continues along that we're seeing a reduction in the mass on areas like West Antarctica due to melting of ice sheets, and also Greenland. So to produce a map of the time-varying gravity field, like I showed before, from the GRACE observations, what we need to do is model the orbits of the satellites using the observations from the satellites and background models of the known gravitational accelerations which act on each of the satellites. So these include things like the Earth's static gravity field, but also the gravitational effects of other planetary bodies in the solar system, changes in atmospheric pressures, ocean tides and currents, and also non-gravitational accelerations, which I'll get into a little bit later. So in order to then extract what we're interested in, that being the temporal gravity field, what we need to do is difference the modelled orbits and the actual GRACE observations, so we can then extract those time-varying signals. So this is a quick example of a single day where the lines show the ground track of the satellites as they orbit around the Earth. And what I'm showing here is the double time derivative of the distance between the satellites, which we call the range acceleration, and that's what we use as our observation when we invert to solve for the gravity field. So on a good day, what we see here in the range acceleration residuals, all of the signal that you can see is mostly in areas that are that have high variation in water masses, such as the Amazon basin and West Antarctica. When we stack up 10 days, for example, and fill in all of that white space with observations, we can then eventually use those measurements in our inversion to solve for the temporal gravity field. But unfortunately, we often come across days that look like this. These results don't really make any sense. There's this weird once per revolution variation in there that isn't that doesn't describe any time varying change in the Earth's gravity field. So it turns out that the non-gravitational accelerations, we need to calibrate those in orbit integration when we model our orbits, otherwise we end up with lots of error in our modelled orbits. What the accelerometers do is they measure the non-gravitational accelerations, and they sit at the center of mass of each of the satellites, and we have to calibrate these for bias and scale. Now, these measurements also contain a fair bit of noise, but on a good day, the observations appear the way they are on the right, where the along track, cross track, and radial axes, which are labeled on the left here, sort of vary as they orbit around the Earth. Now, when we interrogate the data for the bad day that I showed before, it turns out that across this 10-day period, we have this really weird long wavelength variation in the accelerations. So the blue line is the cross-track accelerations. That's mostly measuring the solar radiation pressure. And we can see that there's this 500 nanometer per second squared variation, which doesn't really make any sense. We've also got some smaller long wavelength variation in the along track, which is, as it turns out, caused by a thermal variation. Now, for the accelerometers to operate optimally, they need to be kept in a thermally stable environment, but sometimes that's not always achieved. So these are the observations that come out of the day that I showed before. And in this particular day, we only see a little bit of thermal variation, but we can see that even just that small amount of thermal variation really ends up stuffing up our orbits. So this temperature-induced long wavelength noise that I'm showing here is what I call bias drift. And we see that often post-April 2011 for pretty much the whole second half of the GRACE mission, which means that many, if not the majority of our observations contain this bias drift, and we can't really use that for estimates of the temporal gravity field. So what I did was I developed a filter, which I won't go into the details of, but essentially I low pass filter the cross-track accelerations, and that pulls out really accurately the thermally induced bias drift. Then I remove that from the raw observations and end up with this, these cleaned up accelerations on the bottom left. Now, unfortunately, I can't simply use the same method on the along track, as the frequencies that contain the bias drift and the along track accelerations also contain real geophysical signal. So instead, what I did was developed a transfer function which scales this black line, which is representative of the cross-track bias drift to the along track. And removing that from the raw observations produces a nice noise-free observation. So this is looking at what we looked at before on the left. When I don't filter the accelerometer measurements, we end up with results that don't really make sense. The range acceleration residuals aren't showing up nicely, those temporal gravity field signals. On the right, when I use the filter, we really accurately, we can already pull out the signals in there that are caused by things like the masses of water in the Amazon basin, and you can sort of just start to pick out mass loss there in West Antarctica. So when I stack 10 days worth of the unfiltered observations together and invert for the gravity field, we end up with an estimate of the temporal gravity field that doesn't make a whole lot of sense. There's a lot of this north-south striping, which we can't really explain with any natural process, when instead I use the filtered observations that I filtered prior to modeling the orbits, and then using them to invert for the temporal gravity field. We completely remove that north-south striping, and now it becomes really obvious where mass loss is occurring, or there are variations in groundwater and surface water masses. And essentially, what I want to get across here is that this method works really well, and we apply it to every single day of observations, regardless of whether or not the long wavelength noise exists. And I'm almost ready to submit these results to advances in space research.
I'm going to unmute myself now.
Mm-hmm.
Thank you very much for that, Beck. It was a very interesting presentation. If anyone has any questions, please feel free to put them in the chat. But we need to move to the next talk, which is by Yamila. She's talking about the magma fertility and fieldwork in the Andes and central Chile.
All right. Can you see my screen?
Yes.
Okay. So, today I'm going. Sorry, it's just it's having troubles. Oh, there it goes. All right. So thank you very much for still being here, listening, and two little things around. Okay, so my name is Yamila Cajal. I'm a third-year PhD student. I'm working under the supervision of Professor Ian Campbell, and I'm part of the petrology group. And today I'm going to talk like in general terms about what my PhD research is about, and also a little bit about how was the experience of conducting a fieldwork in central Chile, which I did early this year. So what do? I work in subduction zones where igneous rocks are formed, and I'm particularly interested in intrusive to subvolcanic rocks, which are formed in this area here. And why I'm interested in this area is because there's where usually like the intrusions related to porphyry copper deposits are formed. So the intrusions formed there can be absolutely not related to ore mineralization, which we usually call barren, or that can actually relate it to ore, which we will call ore-bearing intrusions. So for example, in this picture, we can see very little, like there's some chalcopyrite here, which is a copper mineralization. So then we call magma fertility to the capability of the magma to produce or not rocks related to an ore deposit. And why is this important? This is because understanding what controls the fertility of the magma can help us to distinguish between these two types of intrusions in early stages of mineral exploration, saving a lot of time, resources, and money. And how do we do that? So in this case, it seems quite obvious because we are looking at the mineralization here, but this is not always the case. And sometimes we can have rocks like this one, which are actually related to huge copper deposits. So obviously there are many different approaches to answer these questions because there are many different factors that control magma fertility. My approach is through the study of the magma, of the chemistry of these intrusions. And what I do with my samples is that I reduce their size until rock powder. And then I perform all the different laboratory techniques in order to get the different concentrations of chemicals. Then with the concentration of the chemical elements, I plot them into different chemical diagrams in order to understand the chemical behavior and the magmatic evolution of the magma that form these rocks. So for example, here there is a discrimination diagram that uses palladium and platinum concentrations to discriminate between barren and ore-bearing intrusions. So for example, for rocks like these ones, we expect it to be plotted in the barren field, whether for rocks like this one, we expect it to have a plot in the porphyry-related field. It is not always the case, but these type of diagrams are trying to predict these situations. Why using this type of diagrams is important is because they can help us to discriminate between barren and ore-bearing intrusions in early stages of mineral exploration, which means that they could possibly be used as potential exploration tools to either discard or not prospective areas. So my area of study is the Andes of central Chile. I am studying rock samples from the Rio Blanco and El Teniente to the north, which are porphyry copper deposits, and also from La Invernada and Cerro Risco Valle Huemul plutonic complexes to the south, which as far as we know, they are absolutely not related to copper deposits. So my idea is to compare the geochemistry of these two known deposits with the two non-mineralized plutons. So all these cases of studies are located in the Andean Cordillera, here, and they have been formed under similar tectonic conditions during the late Miocene to the early Pliocene, and they're also hosted by Miocene volcanic and volcanic classic rocks. So for this reason, because they're sharing quite similar geology setting, we believe they're actually comparable. The samples from the Rio Blanco and Teniente deposits were collected during 3 visits to the mines. They are from drill cores, and they were collected thanks to the collaboration with Codelco Mining Company. The samples from the Barren Suite early this year during a field trip that I performed, and this is what I'm going to talk during the rest of the talk. So the idea of doing this fieldwork came in late 2018 when I attended the conference in Chile. And there I had the chance to have an informal meeting with geologists from the Chilean Geological Survey and from the University of Chile, who are also working in this area, but from different approaches. So we thought it was a great idea to actually join forces and collaborate between us. So then the next step was actually getting funds for performing this fieldwork. And for that reason, I applied to the Society of Economic Geologists student grant, which I got, and I strongly recommend to apply to anyone working in economic geology. This grant allowed me to cover most of the expenses related to the fieldwork, which were shared with the funds from my collaborators. After that, we were actually able to start planning the field trip, deciding where to go, which areas we wanted to visit, how we're going to get there, what we need, etc. And I have to say that planning this fieldwork was actually very challenging, not only because I was doing it from the distance, but also because this is a very remote area where there's not much information, there is not many access. So at the end, we have to get closer to the areas using 4-wheel cars. But then to actually access the area, we had to rent horses and ride also for a couple of hours. So, and obviously sleeping in tents in the middle of nowhere. But all these challenges were actually it made the whole experience a lot more enjoyable, and it was actually a lot of fun. I also have to say that our initial plan was a little bit too optimistic because we were not really aware how difficult the access were. But in reality, we didn't really manage to visit all the different places we wanted, because sometimes we had to spend the whole day just for getting 2 samples, riding horses for a couple of hours and then walking up to the mountains for another couple of hours. And before then we have to actually come back with all the samples and everything, but this was definitely worth it. So at the end, I managed to collect most of the samples of the relevant areas that I needed, but it was also an amazing experience, not only because I have the opportunity to visit all these beautiful places, but especially because working with this team of people allowed me to learn from their expertise, like structural geology and stratigraphy, which are not my main topic of research, but this helped me a lot to understand much better the geology of the area. So also a science such a remote area made me realize that we know about this region is still very limited and there are a lot of things to do. So finally, my samples made it to arrive in Australia. I collected 29 rock samples from both intrusive complexes. They cover compositions that go from gabbros to high silica granites. What I'm doing now is actually reviewing these samples and the thin section that I already prepared for all the subsequent chemical analysis. And after that, I will be conducting all the necessary laboratory work, which will include petrological, geochemical, and geochronological studies, which will be followed by the corresponding data processing and interpretation. And obviously, all the results obtained will be compared with those from the porphyry copper deposits. And finally, I just want to share some pictures of the people and animals that went with me to the field trip, because without them, this wouldn't be possible. I'm happy to take questions.
Thank you for your talk, Emily. It was really good. We have time for one question, if anyone would like to submit them right now.
I will stop sharing.
Okay, then we can move to the next presentation if no one has any questions. The next person presenting is Shubham. He is detecting earthquakes around the Lake Erie in South Australia.
Yeah, that's great. Thanks, Stu. I'll share my screen. Can you see?
Yes, I can see it.
And my voice is all right? Cool. Good afternoon, everyone. Thank you for taking the talk, and thank you for the organizers of StuCon for jotting this cool 3 days so that we can practice. So as Lou mentioned, the title of the talk says detecting earthquakes around Lake Eyre, South Australia. And I'm working with Dr. Caroline Eakin in seismology and mathematical geophysics group. So when we think about Australia, we don't necessarily think about earthquakes, right? But since 1840, as you can see from this map, there have been a handful of earthquakes, to say the least, in mainland Australia, and which are marked by the colors. So the red ones and warmer colors are which are closer to today, or more recent ones per se. And we can see that they occur basically in most areas of Australia. And one of the reasons, or one of the explanations which have been put forward to explain these is the presence of active plate boundaries around Australia, and these tectonic forces could be translated or transmitted to the just give me a second. Sorry, just one sec. Yeah, so these active plate boundary forces could be translated to within the Australian plate and could result in generation of earthquakes. However, this is just one of the hypotheses. So my area of interest is South Australia, specifically here. And you can see that there is a perceived gap of seismicity here. So if we have a closer look around this area, so again, this is the same zoomed in version in Australia, Adelaide for reference, and the earthquakes here are blue and cyan and green colors. You can again see that this gap in seismicity is amplified here. Two more things to note here is that in the same region, two of the major earthquakes have happened. So the most recent large earthquake, Peterman's earthquakes, happened just northwest of this region, and the third largest magnitude earthquakes in the Simpson Desert, just north of here as well. So is there actually a gap in seismicity here, or is this a manifestation of lack of seismic stations? So what you're looking here is a map of all the seismic stations in Australia, and you can see that this region has not been covered. So the first motivation to study this area is, was there a gap, or is just because of the lack of coverage? And the second was a drastic change in the crustal depth in this region. So what you're looking here is a map of the crustal depth for whole Australia. This work was done here at RSCS earlier in the last decade. And you can see that on the west, which is the Gawler Craton, you have quite a deep crustal thickness, which is around like 50. And then when you come to Lake Eyre, it suddenly drops to 20. So how come there is such a stark change in the crustal thickness? And does this result in some earthquake generation in this area coming from Gawler Craton to Lake Eyre? So these two are the main motivation, and also to look at the earth beneath and to image. There was a OSCO-funded project which deployed 40 seismometer in that region over a course of 2018 and 19 seismometers. And the last 5 or 6 of them were deployed in Simpson Desert, which actually needed a helicopter to be deployed. So if we have a look at what the deployment looks like, so again, a similar region of Australia, Adelaide for reference, and these are the 40 stations which were deployed. And this is Flinders Range, and the topography is exaggerated. It doesn't actually look this drastic in real life. So we have the stations deployed. How do we go on detecting the earthquake? So if I can oversimplify the process, and I've divided into 3 parts. First, looking at the data that is collected and try to get the best out of them, how to separate an earthquake from the rest of the noise, which has been continuously recorded. And once we have that, how do we actually go on locating the event? So the first part is looking at the seismograms. So lot of times when you have a seismogram, this would be like how it would look like raw. But if we extract useful information out of it and some manipulation, it would look like this. So this is 1 hour of data on 11th November 2018, and you can manually, you can just visually pick out there is a clear earthquake event here. So I do this for all the stations, all the data recorded. The next step is how do we separate this energy, the earthquake energy, from the background noise? So we can do it manually. However, when you have 40 stations and you have 2 years of data, you can't just go and look at all the data manually. Also, it's not totally objective to do that. So I'm using a method which is quite classical, which uses the concept of just varying energy in a seismogram. So what I do is calculate the short-term energy. So imagine this blue box right here. So I will calculate some of the energy of coming within this box and term it as short-term energy, which is sensitive to the earthquakes or instant amplitude increase. And another, I would have a longer window, longer moving window, which would be sensitive to the background noise. And when I divide these two energy, I would get a parameter, which is the ratio of these two, which I use as a detection threshold. So you can see here that as the earthquake arrived here, the algorithm picks up the P waves, and the S wave is not picked here, but I just show here that it could be picked from the other components of the seismogram. So this is basically what I do for all of these, all the data. However, even after you get the arrivals, how do you bring them together to get the earthquake? So I use an algorithm which was recently developed. So I provide this algorithm all the arrival information or when the energy basically arrives. And this algorithm does the work for me to find the location where the earthquake could have happened. So now, let's say we have the earthquake location. So I'm in the process currently of making the earthquake location. So if we zoom out and think, why am I doing this, or why are we doing this? So, or other question we can ask is, why is this even happening? Why are these earthquakes happening, or what is making them happen? So the second question is, when we have the location, which we will try to address, is what is the physical mechanism behind it? And if they're occurring, but why are they occurring in the places they're occurring and not anywhere else? So this would be the follow-up questions which I would be addressing soon after. Thank you.
Great talk. Thank you very much. Does anyone have any questions?
Sorry.
If no one has any questions, we can move forward to the next presentation.
Thanks, Lou.
Thank you very much. So the next person presenting is Bruno. He's presenting on the alkali metals in chondrites, Cluson nebular, and parent body processes. If you can share your screen. Thank you.
Hi, good afternoon. So yes, I'll be presenting on my project, alkali metals in chondrites, Cluson nebular, and parent body processes. So first of all, why the interest in alkali metals? Well, first, they're lithophile, so their chemistry is very easy in geological settings. Then they are moderately volatile in nebular conditions. So the 50% condensation temperatures, nebular conditions will be between 1135 to 800 Kelvin. And we have the advantage that both lithium and potassium can not only be measured for abundance with the shrimp, but we can also measure isotopic composition. So lithium isotopes can tell us a lot of things, but one of the key things that they can tell us is aqueous alteration. So OIB is more arc magnetism, and the mantle, they all have lithium delta 7 compositions between 2.4 to 7.9 per mole. And for example, upper continental crust has a per mole value of 0.6. So what happens during aqueous alteration is that the lithium-6, so lithium has two isotopes, 7 and 6. Lithium-6 is preferentially retained in the minerals, while lithium-7 ends up in the fluid, in this case, water. So that's why rivers have per mole values between 1 and 44. And the ocean has per mole values of 31. So if we alter, for example, MORB, that is 3.4, with seawater, because it has such a high lithium-7 content, even though lithium-6 prefers to incorporate into the alteration minerals, we will still have a higher value, so 5.6 in this case. Potassium, on the other hand, is a bit different. So it still changes with different settings, but it's very difficult to distinguish the signature from igneous to sedimentary. So the easiest ones to identify are hydrothermal minerals. They usually tend to have lighter values, and evaporites have higher values. So they cannot tell us much, potassium cannot tell us much about aqueous alteration, but it can tell us about Rayleigh distillation. So Rayleigh distillation is when the material is at a temperature very close to the condensation temperature. You will preferentially evaporate the lighter isotope and retain the heavier isotope. So it creates a change in the isotopic ratio that we can measure. In the case of potassium, we use potassium 41 and 39. So potassium 39 will be preferentially lost in this evaporation process. And it has been proven that that occurs for Martian, lunar, and western samples. So these are meteorites that are very similar to basaltic rocks. So what happened most likely was that when they erupted or they were melted, some of this potassium 39 evaporated faster than the potassium 41, and that's why we get these heavy isotopic signatures. So how this all relates to chondrites comes from the chondrite formation. So chondrites have three main components, as you've heard today. CAIs are the first one to form. So these are condensates from the solar nebula, so high temperature. So they are mostly calcium and aluminum, and they contain other refractory elements. So the alkali metals have condensation temperatures that are a bit too low for condensating in CAIs. But for example, in chondrules, which are conglomerates of dust, so kind of grains that get melted and then cooled down in very short timescales, geologically speaking. These ones could show some signatures for Rayleigh distillation. In contrast, the matrix, which is the last main component, it's just dust from the solar nebula. So this one would have escaped this thermal processing, and then it could show a different isotopic composition. But the story doesn't end there. So once we have a chondrite form, so we have our CAIs, our chondrules, and our matrix together, this chondrite can also get altered. So one of the alterations is aqueous alteration, or we can have metamorphism. And they're not mutually exclusive. So we can have a meteorite that first underwent hydration and then metamorphism, or the other way around. So the idea of my project is to first identify the host phases for the alkali metals in type 3 and type 6 chondrites. So type 3 will be chondrites that experience very little or no alteration, so either aqueous or metamorphism. And type 6 chondrites will experience only, so that will be the far end of the metamorphism. So once I identify the phases in those two groups, the idea is to measure the alkali metal abundance, see if they have equilibrated through the metamorphism, and also see how they distributed between chondrules and matrix. And then finally, in some phases, preferentially alkali metal rich, the idea is to measure some of the lithium and potassium isotopic compositions and then try to see which process affected the alkali metals and therefore the chondrite. So if lithium can tell us about hydration, whereas potassium probably is a better proxy for partial evaporation. And if you've been wondering what's the photo in the background this whole time, this is a ordinary chondrite type 6 that fell last year in Cuba. It's called Viñales, and here you see the fireball from the Havana harbor. Thanks very much. That's all the presentation.
Oh, awesome. Thank you very much for your presentation, Bruno. Does anyone have any questions?
I was wondering if I could ask a quick question.
Yes.
How did you go about measuring the isotopes? Well, which machine did you use for measuring the potassium and the lithium?
So up to now, the predominant method for both lithium and potassium has been ICP-MS in solution, so not laser ablation. There have been some measurements with shrimp, but the problem with shrimp is that we will need to do matrix correction for the phases. So during my project, I will probably end up doing some ICP-MS to calibrate some standards, and then with the shrimp do the measurements on the actual samples.
Huh, that's pretty cool. Thank you. And yeah, love the background too, by the way. That's pretty cool.
A follow-up one, Bruno. So if both of these elements can be measured on front, why not laser ablation?
For potassium, the potassium has a problem that in laser ablation we will use argon as a carrier gas, and argon has a argon 40, which is the predominant isotope, and that will have a very major peak. So we're trying to measure, get the least amount of interferences. So for potassium, that will be a problem. And for lithium, there have been some early some studies that have done laser ablation, but at the same time, we will need some standards to be sure that there's no matrix effect happening.
You also have a question on the chat. If there's lithium and potassium isotope variations in meteorites, primarily there are also variations in rhodium isotopic composition, but is it too obscured by the effects of radioactive decay?
Sorry, I didn't hear which element.
It's in the chat, the question.
Oh, sorry. So with rubidium, the problem, so rubidium can be measured with ICP-MS. It does show even stronger correlation with radioactive distillation because it has a lower condensation temperature than potassium. The only problem is that in shrimp, it cannot be measured in silicate phases. So that's why I didn't mention it. So ideally, we would love to measure rubidium, but unless we measure non-silicates, it will be very difficult, or basically impossible due to interference.
Okay, I think if no one has any questions, we can wrap it up. I will ask any of the academics that watch the talks if you can send in the judging sheets to Jess Hargreaves or to myself. And if you can do that as soon as possible, because we want to announce the winners within the next 10 minutes. I would also like to remind, if anyone is going today to the gathering, please sign up. And we're also gonna have a poll on the chat so we can choose the students, the best student presentation. And so the poll is on the chat, and I'll give you 2 minutes to do that. And after that, I'm gonna present the winners for this photo competition.
Could I just thank all of the students for participating in this online conference, and thank in particular the people who have organised it. This has run absolutely seamlessly. There have been very few issues or problems. I know from chairing online meetings and so on how difficult this is, and this has been a really stellar professional performance by you guys. So congratulations, pat yourselves on the back, and well done for all the wonderful presentations that everyone has done.
Thank you, Paul. Give it a couple more minutes because I think people are having trouble. Yeah. Is everyone having trouble submitting their vote? We've got 8 votes. Oh. So people are managing.
It's saying that some of the options are unavailable, which I think
seems
is
that
what
if
the
someone's
issue is.
already voted for that person, you can't vote for them a second time.
Okay.
Oh. I might have stuffed this up.
It means everyone's a winner.
Yay. Okay, hang on.
Yeah, because I was like looking, because I can't pick, like, for example, I can't pick Jess's talk and I can't pick
Okay, I'll fix it. I'll fix it. Maybe we'll present the photo competition awards and I'll get it sorted and then resend it.
Yeah, that would be a good idea.
Okay, so, well, that's getting sorted out. We're still waiting for any of the academics to submit their scores, but we can begin with the who wins the photo competition. So we're gonna begin with RSCS in the field, and the winner is Catherine. This was a beautiful image, and we're gonna be distributing the prizes later today. Congratulations. Then the next one is RSCS in the lab. The winner was Adi. With this, when you look at it under the microscope and it looks back at you. That's a very nice one. And we already put all the pictures downstairs. So when you walk in the foyer, you can see all the submissions. They're pretty cool pictures. And then RSCS on holiday. Stacy Martin, congrats. With the Caldera Paradise. This is beautiful. It's a great picture. And then the final one is the overall winner from the picture that got the most votes, whether it was on holiday, on the field, or samples. It's Radesh with double exposure. Wow. You can all get your prizes later today. we're gonna be distributing them. Now, we're gonna go on and present the student awards. Let me get your computer.
Okay, have people managed to cast a vote now that I've changed the settings on the poll? I'll give it a couple more minutes. No, I think it should have maintained, yeah, it retained all of the votes that had already been made. So if you'd voted already, that's all good. But if you found that you couldn't vote before, you should be able to now. Okay, so we'll close the votes there. And I am happy to announce the best talk for day 1 was Jess Hargraves with Reading the Reef. And the best talk for day 2 was, where are we, sorry. The best talk for day 2 was Caleb Bishop, tracing the evolution of early Archaeoplastuda through the Cryogenian glaciations. And I believe Lou has the result for day 3.
I only got it from one day. I don't know if anyone sent it to Jess as well.
She didn't.
She did? No one sent? Okay. Should I tell it to you? Or here, what do you mean? I know.
Okay, and the best talk for day 3 was Yamila with her talk, Magma Fertility and Fieldwork in the Andes of Central Chile. And the best overall talk was Riley with Thermodynamic Modeling of Low Temperature Mineral Formation in the Tagish Lake Meteorite. So congratulations to everyone who won best talks. Really well deserved. There are some great prizes thanks to Boz. Boz put together some hampers for everyone. They'll all be in the reception for all those people to collect, anyone that won a photo award or the talk awards. And while I've still got everyone, I just wanted to thank all of the organisation committee for helping get this going this year, and thank you to everyone who decided to do a talk. It seems that we pretty much got through the 3 days without a hitch. The first of, I think the one and only technical difficulty we had was today with Lou and I trying to present and chair in the same room. So that's pretty good, I reckon. And hopefully see everyone out in the courtyard for drinks.